Hello everyone, I'm Falk, and in this talk, I'll share my journey from investigating the algorithmic principles of human intelligence to developing digital interventions for improving human decision-making. I embarked on this journey because I'm inspired by the human potential for developing a grand vision for a better future and then turning it into reality. All of us are endowed with this capacity, but sadly, many people struggle to realize their full potential. I believe that cognitive science can help us understand the challenges of living a good life in computational terms and thereby inspire new ideas for how we can help people master those challenges more successfully. I started my journey to improving human decision-making by investigating which cognitive strategies might enable good decision makers to make thousands of excellent choices every day. After having discovered some of those strategies, I became curious how people might be able to learn them. This led my team and me to reverse engineer the mechanisms of metacognitive learning in terms of machine learning algorithms that advance the state of the art. We then combined these machine learning algorithms with the principle of resource rationality to automatically discover optimal strategies for human decision making. And we created intelligent tutors that teach those strategies to people so that they can make better choices. I will start by introducing our theoretical framework for understanding and improving human cognition. We developed this framework to improve traditional notions of rationality, such as expected utility theory. If expected utility theory gave you advice for how to make a decision, it would say that you should choose the option that has the highest expected utility in expectation over all of the scenarios that might happen. While this is a viable solution for simple textbook problems like this one, it is no longer a viable solution for real-life decision-making, such as choosing a career. In fact, if you applied the strategy of calculating expected utilities to choosing a career in a literal way, you would not have a career. To address this flaw in traditional notions of rationality, we propose an alternative normative principle. This principle is, make the best possible use of your finite time and your bounded cognitive resources. We call this principle resource rationality. Resource rationality is a mathematically precise normative principle for real people who only have a limited amount of time and a bounded amount of cognitive resources and yet have to make thousands of decisions every day. This includes small decisions such as whether to have another cookie, as well as larger decisions such as what to work on. According to this principle, people should decide by using those heuristics that achieve the best possible speed-accuracy trade-off for each type of decision. We formalize this idea by building on the mathematics of bounded optimality and rational meta reasoning that was developed to design optimal agents for performance-limited hardware. Applying this principle to cognitive strategy suggests that we can find the optimal heuristic H star by solving this constrained optimization problem, where the strategy is constrained to be implementable by the brain, and the objective function is the expected utility of the consequences that will result from applying it in the current situation, in the current environment, minus the expected opportunity cost of the time that it will take the strategy to arrive at a plan or decision. In many cases, the optimal heuristic H star turns out to be very simple. For instance, when we applied the principle of resource rationality to a particular class of risky choice problems, it rediscovered the popular take the best heuristic. This heuristic chooses between multiple alternatives based on just one single criterion. Unlike in this case, applying the principle of resource rationality usually leads to novel heuristics that were previously unknown. For instance, when we applied it to a very simple model of sequential decision problems that people face in the real world, it discovered the future first heuristic. According to this heuristic, we should choose between alternative courses of actions not based on their immediate or short-term consequences, but only based on their long-term consequences. This is just two examples of a very long list of heuristics that can be discovered by applying the principle of resource rationality. We've applied this principle to problems in judgment under uncertainty, decision-making from experience, and decision-making from description, and planning. And we found that the resulting resource rational heuristics explained a wide range of empirical phenomena, including the cognitive biases, such as people's tendency to be overly swayed by extreme eventualities that come to mind easily, and people's tendency to be biased towards those estimates that come to their mind first. These biases were previously thought to be incompatible with human rationality. By contrast, our resource rational perspective suggests that they might reflect the rational use of finite time and bounded cognitive resources. After having found that people use resource rational heuristics, I became curious how they might learn them. This led me and my team to reverse engineer the mechanisms of metacognitive learning. Metacognitive learning is the distinctive aspect of human intelligence that enables us to discover and continuously refine our own algorithms. We are born not knowing how to control our bodies, let alone our minds, but over the course of our development, we discover very sophisticated ways of thinking that are more effective than the best algorithms that computer scientists have been able to come up with so far. To get there, the brain has to solve numerous algorithm discovery problems throughout its development, and metacognitive learning is the set of mechanisms that makes this possible. My working hypothesis is that metacognitive learning leverages the rewards that we experience as a consequence of our decisions to then refine the cognitive strategies that generated those decisions. To reverse engineer the mechanisms of metacognitive learning, we conducted a series of experiments where people solve a sequence of planning problems, and we then observe how their planning strategy changes from the first trial to the second trial to the third trial and so on, and we develop computational models of those changes. As you can see by looking at the orange line, people discover increasingly more effective planning strategies as they repeatedly plan in the same environment. And as you can see by looking at the blue curve, we were able to develop a model called the Learned Value of Computation model, or LVOC model for short, that accurately captures this capacity for strategy discovery. According to this model, metacognitive learning is a form of reinforcement learning wherein people backpropagate the reward they experience as a consequence of their decisions to the individual computations that led them to make those decisions. Concretely, the LVOC model learns to predict the value of performing a planning operation C in a belief state B by a weighted average of features of that computation. These features include how attractive the path was that this computation explored, how often it had been performed in the past, how much it reduced the uncertainty about the value of that path, and how many steps it looked into the future, along with many additional features. We subsequently extended this model into a machine learning algorithm for discovering efficient algorithms. We applied it to a number of benchmarks, including algorithm discovery for planning in binary trees. And as you can see by comparing the blue bar, which represents the performance of our method, to the red bar and the purple bar representing the performance of the previous state of the art, our method significantly outperformed the best prior methods from artificial intelligence. Encouraged by these results, we then combined our method with the principle of resource rationality into automatic methods for discovering optimal cognitive strategies for people. And we developed intelligent tutors that teach those strategies to people to enable them to make better decisions. The basic idea is to model the decision problems that people face in everyday life and the cognitive architecture that they have available to make those decisions as a meta-level Markov decision process. And then apply our meta-level reinforcement learning methods to discover optimal cognitive strategies. Having discovered those strategies, we can then create intelligent cognitive tutors that teach those strategies to people so that they can use them to make better choices. As a proof of concept, we apply this approach to a very simple model of planning. This model captures that the immediate rewards for our actions tend to be small compared to the long-term rewards that we can attain through a series of coordinated actions. It also captures that planning takes time and time is costly. We found that under those assumptions, the optimal planning strategy is the future-first heuristic, illustrated in this video. As you can see, it chooses a course of action by inspecting its long-term consequences. This is not the strategy that people intuitively use in this task. Rather, people often choose on the immediate rewards without inspecting the long-term consequences. To help people overcome this irrational bias, we develop an intelligent cognitive tutor that poses people planning problems, observes their planning strategy, and then gives them optimal metacognitive feedback that is designed to maximally accelerate the metacognitive reinforcement learning towards the optimal cognitive strategy. To get a sense of what it is like to practice planning with the intelligent tutor, please take a look at the following video. As you saw, our intelligent tutor gives people immediate metacognitive feedback after every click. This feedback has two components. The affective component makes people feel how good or how bad their planning operation was. And the informational component lets them know what the optimal planning strategy would have done. As you can see, by looking at the green curve, the tutor's feedback enabled people to very rapidly improve their planning skills. By contrast, the control condition improved at a much slower rate. This benefit was retained after the tutor was removed and everybody was tested on the same problems. We found that the improvements result from people gradually discovering the future first heuristic and unlearning suboptimal heuristics. And furthermore, this process is substantially boosted by the feedback of our intelligent tutor. Furthermore, we find that people transfer the strategies that they discovered by practicing with the intelligent tutor to more complex planning problems that are more like the real world. Furthermore, the resulting improvement in planning performance is retained after at least 24 hours. In summary, I developed a theoretical framework for understanding and promoting good decision-making. On this journey, I reverse engineered how people discover cognitive strategies. This led to a machine learning algorithm for automatic strategy discovery, and we leveraged it to create intelligent tutors that discover and teach strategies for good planning. I'm now continuing this line of research with the Rationality Enhancement Group. We are based at the Max Planck Institute for Intelligent Systems in Tübingen, and we currently have an open position for a PhD student or postdoc interested in metacognitive learning. Our mission is to lay the cognitive and technological foundation for helping people improve themselves, live a good life, and make valuable contributions to society. To lay the cognitive foundation for life improvement science, we study the mechanisms of goal setting, goal achievement, and metacognitive learning. To lay the technological foundation for life improvement, we develop intelligent digital assistants that help people set better goals, achieve them, and improve themselves. With this, I'd like to thank my PhD advisor, Tom Griffiths, our numerous collaborators, including Fred Callaway, the Rationality Enhancement Group, the Glushko Dissertation Prize Committee, and the people who recommended me for this prize. Thank you very much for your attention. I'm looking forward to your questions.